Hello all. Today we will see the second lecture, which is about DC motors. DC motor is a machine that converts electrical energy into mechanical energy. The input power is an electrical energy from a battery, and the output power is mechanical energy. By supplying DC power, voltage, and current, we have the interaction between flux and current will result in the motion of the motor, which is its rotation with the speed in revolutions per minute. The DC motor has the same construction of DC generator. They are the same devices. They are different only in the input and output power. In both modes of operation, the amount of power converted from mechanical to electrical or the vice versa is given by power developed equals EA, which is the back-induced EMF inside the DC machine, times the IA, which is the armature current of the machine. To understand the difference in action between motoring and generating, this can be well demonstrated by the two figures shown here. For the generator, the back-induced EMF EA is the source of the current, where IA is originating from the back-induced EMF EA to the outside circuit, which is the V terminal or the load, the electrical load. Here we have the back-induced EMF EA is bigger than the V terminal, while for the motor, we have the current entering from the V terminal, which is the battery, entering to the machine, and the back-induced EMF here is lower than the V terminal or the battery voltage. For the back-induced EMF equation, as we have seen in the generator, equals the motor constant K times the flux in Weber times the rotational speed in radians per second. And for the induced torque or the developed torque equals to the same constant K times the flux of the machine multiplied by the armature current, which is IA. For the motor constant K equals P, which is the number of poles, times Z, which is the number of conductors, divided by 2 pi times A, which is equal to the number of parallel pulses in the machine. Omega is the speed of the armature in radian per second, and phi is the flux per pole in Weber. IA is armature current, and Ka or K is the machine constant. The power developed equals EA times IA, and from the mechanical point of view is equal to the torque developed times omega. If we need to calculate torque developed, we can obtain it by dividing the power developed by omega. The power developed equals to EA times IA divided by omega. We get the torque developed in Newton meters. For the generator is driven by a prime mover, which is any type of turbines. The turbine has a torque, which is torque of the prime mover, torque subscript PM, and the generator has the back-induced EMF EA and the electromagnetic developed torque developed, which is opposite in direction to the torque induced or impressed by the prime mover, so that the shaft of the generator will be rotating with a constant speed omega m. For the terminals of the generator, it will have a V load or V terminal, and it draw a current IA as shown in this figure. We have EA, the back-induced EMF, VL is the load voltage, torque subscript PM is the torque generated by the prime mover or the driving torque for the generator impressed by the prime mover, and the torque developed is opposing generator torque or the electromagnetic torque, which is opposite to the prime mover torque. For the interaction between the DC motor and the mechanical load, we have the DC motor is driven by an external source, which is the battery with voltage V load or V terminal, and the motor draws a current from the source equals IA, and a back-induced EMF EA is developed inside the DC motor, which is converted along with IA, which is the power developed, to the power mechanical, um, and we get the torque developed, which is the torque driven by the DC motor, uh, which is connected to the load. We have the mechanical load, which can be a pump or a compressor or a fan, which is having a torque, which is a low torque. The low torque is opposite in direction to the torque developed, so that they have equal magnitudes in opposite directions, and the motor will be rotating with speed omega. For the V load is the applied voltage. The load torque is opposing load torque, and the back induced EMF EA is the back induced EMF. Torque developed is the torque developed by the DC motor. For the classification of DC motors, we can classify DC motors from the point of view of the connection of the field. We have the first connection, or the first classification is separately excited DC motor, where the field winding is connected to a battery and the armature is connected to another battery. So the field is separately excited over an external circuit, not energized by the back-induced EMF. For the second connection is a shunt-excited DC motor. We have the shunt field winding, which is connected in parallel with the armature, which is composed of the back-induced EMF and resistance of the armature, and all of these are connected in parallel to the supply voltage, which is the battery. The third category or classification is the series excited DC motor, where the armature and field are connected in series, and this field winding is different from the shunt field winding, and we will see this in the next slides. For the next type is the compound excited DC motor. We have the shunt field winding, which is connected to in parallel with the armature, and we have also the series field winding connected in series with this combination, and the battery is connected to this external circuit. For the compound, we may have commutative compound and differential compound according to the interaction of the fields of the series and field windings. Um, the series field winding must have low resistance, while the shunt field winding must have high resistance. Why? The shunt field winding has big number of turns, or a huge number of turns with a small cross-sectional area, so that its resistance will be high. And for the series field winding, it has a small number of turns and big cross-sectional area, which produce a low resistance. Why the shunt or separately field winding resistance must be high? It is connected in parallel with the supply, so it must have a high resistance so as not to cause a short circuit across the voltage or the source terminals. And for the series field winding, the series field winding is connected in series with the armature and the supply, and if the series field winding has high resistance, it will cause a huge voltage drop or a big voltage drop, and a small share of the V load will be obtained as a back-induced EMF, and we need most of the voltage V terminal to be converted to an induced EMF, so the series field resistance must be low in resistance. The first connection which is a separately excited DC motor, we have the field battery VF and the current drawn from the supply IF and the resistance of the field. For the armature, we have the back induced EMF, the resistance of the armature, and the terminal voltage, which is the voltage of the battery, and we have the load connected with the armature of the machine, which is the mechanical load. In case of motor, we have V terminal bigger than EA, which is V terminal is a battery and EA is a back induced EMF. We have for the field circuit, we have VF equals IF times the resistance of the field winding, which is RF. And for the V terminal, which is bigger than EA, equals EA plus IARA, which is the armature resistance drop, plus 2 delta V, which is the drop across the brushes or the contact between brushes and the commutator. And for the generator, in case of generator, we have EA, which is bigger than the V terminal. EA is the source of the current. We have EA equals V terminal plus IA RA plus 2 delta V, where delta V is the drop across the brushes or the contact between brushes and commutator. Uh, we now need to obtain the torque speed characteristics of the separately excited DC motor. We have EA equals V terminal minus IARA minus 2 delta V, and for EA, which is equal to K, which is the motor constant times phi times omega. We assume here that 2 delta V is approximately 0. Then we will substitute by EA in the equation. We have k phi omega equals V terminal minus IARA. If we divide both sides by k phi, we obtain omega equals V terminal divided by k phi minus IARA divided by k phi. We have the torque developed equals k phi IA. We can substitute IA here by torque divided by k phi. Then we will obtain the omega, which is equal to V terminal divided by k phi minus RA divided by k phi squared times the torque. Here, if the torque equals 0, which is the no load case, then we have the no load speed equals V terminal divided by k phi. This is the no load speed. And as the torque increases, then this part will be subtracted from the no load speed. Then the speed will decrease by the shown value. We obtain the speed at different torques or different loads. Omega naught is the no load speed, which is equal to V terminal divided by k phi at no load or torque, low torque equals 0 Newton meters. For the speed control of separately excited DC motors, we have two ways of speed control. The first way, or the first method, is controlling the terminal voltage. The terminal voltage is directly proportional with the omega. Then increasing the terminal voltage, then we will obtain a higher speed. Here V3 is the biggest one, then omega 3 is the biggest omega, then V2 is smaller than V3, where omega 2 is smaller than omega 3, and V1 is smaller than V2, then omega 3 1 is smaller than omega 2, as shown in figure. This method is suitable or applicable for speeds below the rated speed or the base speed of the machine. If we need to increase the speed beyond or above the rated speed, we have the second option, which is the speed control by field current or field control. We keep V terminal at the rated value and we change or control the flux of the machine or the field current. We have here the field current or the field flux is inversely proportional to omega. As we need to increase the speed, then we will decrease the flux, which is called the field weakening method. Here, the torque and speed we have at certain phi. Omega 3 is the minimum omega, then the torque T3 is bigger than torque T2, then T1. T3 is the biggest, then T2 is smaller, T1 is smaller, as omega 1 is the biggest speed, as the power equals torque times omega. As the torque increases, the speed decreases, and vice versa. Here we can see the two regions of speed control. The voltage control, where the torque is kept constant and the power is increasing by increasing the voltage and increase of omega until the base speed or the rated speed. If we need to increase the speed above the base speed or rated speed, we have the field control where we can decrease the flux. We keep the power constant and keeping the power constant, we have to increase the speed. Then the torque will decrease to keep the power at a constant level up till the maximum speed. The second one is the DC series motor. For the DC series motor, we have V supply or V terminal equals EA plus the drop across the armature resistance and field resistance RA plus RF, where EA equals K times phi times omega, where K equals P times Z divided by 2 pi A. Phi is the flux per pole which is produced by the current of the supply, IS. The relationship between phi and I is the magnetizing curve, which is linear until we reach the saturation, where a further increase in current will increase the flux by a small value. We have torque equals K times IA times phi. For the torque, at the first part, we have I phi is proportional to IS, and the torque is proportional to IS times phi, and phi is proportional to IS. Then the torque is proportional to I squared. Then we have in the first part from 0 to B, the torque is proportional to I squared, which is a parabolic relation. For the part here, we have flux is almost constant due to saturation, then phi is approximately constant, and I increases, then the torque will be proportional to only the current. As phi is constant, we have a linear relation between torque and I supply. For the DC series motor, the speed torque characteristics, we have EA equals K times phi pole times N, and N here is directly proportional with back-induced EMF and inversely proportional to the flux, and the torque is directly proportional to the flux. Then the speed is inversely proportional to the torque, or the torque is inversely proportional to the speed. It is observed that this type of motors has a high starting torque. For a speed equal 0, the starting torque is very huge. The torque is developed at n equal 0, and for the no load, at the torque equals 0, the speed is dangerously high value. Therefore, this type of machines cannot be started without load. Never started unloaded. They must be started carrying a mechanical load. The application of this type of machines depending on high starting torque, such as traction and drilling. For the shunt DC motor, we have the V supply equals back-induced EMF plus IARA, and this is equal to the voltage across the shunt resistance, which is I shunt R shunt. For the current supplied by the source is equal to the I armature plus I shunt. Then we have IS equals IA plus I field or I shunt. The field current, which is I shunt, is constantly maintained as the supply is constant. When Vs is constant and the R shunt is kept constant, then phi for this type of machines is assumed to be constant. We have the speed equals Vs divided by k phi minus Ra times torque divided by k phi squared. The torque equals K times Ia times phi, and K and phi are kept constant. For the variation of the developed torque with respect to the armature current, we have two characteristics. The first one, without armature reaction, the torque and the current are directly proportional as the flux is almost constant. For the case having armature reaction, an increase in the armature reaction or the presence of armature reaction will decrease the flux, then the torque will decrease a bit from the case without armature reaction. For the torque speed characteristics, we have the nodal speed, which is V supply divided by K phi, and this is the line at the nodal speed. We have the speed decreases by the increase of the torque by the part of the torque times R divided by K phi squared. The change in the running speed upon loading is small. We can notice here that the speed will decrease by a small value. It is considered, this type of motors is considered as a constant speed motor. The application of DC shunt motors, which require constant speeds, like lifts, cranes, ladders, and excavators. For the compound motors, we have the first type, which is long shunt. Long shunt, we have the series field is connected in series with the armature, and this combination is connected in parallel with the shunt field, then connected in parallel with the supply. We have the supply current equals I armature plus I shunt, and the V supply equals EA plus IA times the resistance summation, which are series plus RA, and is equal to the parallel voltage across I shunt, which is I shunt R shunt. For the short shunt, we have this armature is connected in parallel with the shunt field. Then this combination is connected in series with the series field resistance to the supply. We have I supply current equals I armature plus I shunt. And for the voltage of the supply equals EA plus IA plus I series or I supply R series, or we have I supply R series plus I shunt R shunt for the external loop. For the flux, which is proportional to N field shunt, I field shunt, which is the ampere turns of the shunt field, plus or minus N field series times I field series, the positive sign for a cumulative compound where the two fluxes are um, increasing each other or in the same direction, and the negative sign for differential compound where the two fluxes are opposite in directions. This is the characteristics between the speed and the torque. For differential compound where the flux increases, then the speed, the flux decreases, I'm sorry, then the speed increases, and for the separately excited is lower, as the flux here is more, then the speed is lower. For the competitive compound, the flux is more, then the speed is lower, and for the series, the torque speed characteristics is inversely proportional. At no load, we have very high speed, and at full load, we have very low speed where the speed drops dramatically. For starting of DC motors, the starting current will be dangerously high due to the small value of RA and the back-induced EMF, where the voltage terminal or the battery is connected directly to the DC supply. For IA equals V terminal minus EA divided by RA, and EA equals K phi omega, and omega here is almost zero, then back-induced EMF will be almost zero. Then IA at the start equals V terminal divided by RA, and RA is very small and V terminal is high, then the starting current is very large. To decrease or limit the starting current to safe values, we have two methods. The first method is increasing or inserting an external resistance at starting in the armature circuit, which is a variable resistance. We have this resistance at a high value at starting to reduce the armature current, and then we reduce it until we reach the value of zero to decrease the current to diminish this resistance and let the motor take the required current. For at speed up, we have IA equals V terminal minus EA divided by RA, which is armature resistance, and R armature external, which is the external resistance added to the armature circuit. For the second method, we have low DC terminal voltage at start as a variable DC supply. This requires a variable voltage supply that can be used in this circuit. At low V terminal, we have low IA at starting, and then we increase the V terminal until we reach the rated voltage of the DC motor. The efficiency of the motor depending on the losses in the DC motor, which is similar to that of generators, which are iron losses, mechanical losses, and copper losses. The power flow diagram for the cases of the DC motor are similar to DC generator with reversed power flow, where the input power here is an electrical power for the separately excited DC motor. This is the power of the battery, and this is the power of the field circuit, which is V field times I field. The first type of losses is the copper losses in the armature, I armature square R armature. Then the remaining power, which is the power developed, which is the power ready for conversion to mechanical power, which is EA times IA, or torque developed times omega. We have the mechanical losses, which is the rotational losses, the friction and windage losses in the bearing and the brush contact with the commutator, and the windage from the rotation of the rotor and the fan. We have the output power, which is the mechanical power, which is the shaft torque times omega motor. The efficiency equals to power output divided by power input, which is equal to the power output plus the total power losses. For the shunt and series motors, we have the power input, which is VS IS, and the first type of losses, which is the copper losses, which is equal to IA square RA, or IF square RF. Then the power remaining for conversion to mechanical power, which is the power developed, equals to EAIA, or the torque developed times omega. Then the mechanical rotational losses, which is the power rotational, and the remaining power after subtracting the power rotational losses from the power developed, which is power output, equals torque shaft times omega m. For the long shunt compound motor, we have the power input, which is V supply, I supply, the copper losses for the armature, I armature square R armature, the copper losses for the series field winding, which is IF series square times RF series, and for the power losses in the shunt field, which is I field shunt square times R field shunt. After subtracting these copper losses, we obtain the power developed, which is EA times IA, or torque developed times omega. The rotational losses is subtracted from the power developed, and we obtain the power output, which is torque shaft times omega. The efficiency is equals power output divided by power output plus power loss. For the input power for the short shunt compound motor, it's the same for the long shunt, which is voltage of the supply times current of the supply. The first is the armature copper loss, IA square RA, and then the field shunt copper loss, I field shunt square R field shunt, and then the series field winding copper losses, which is I field series square R field series. We have the power developed, which is EAIA, or torque developed times omega m. Then we have the power rotational losses, and the remaining power, which is the output power, equals torque shaft times omega motor. The speed control of DC motor we have seen before. The first type is armature voltage control. We have E is less than Vs by the IARA drop, which is usually very small, less than 5%. Then Vs is approximately E, which is P divided by 2 pi times Z over A, which is K, times phi times omega. We have K, which is P times Z divided by 2 pi A, and phi are constants. Then increasing V supply will increase the speed. We have Vs2 is bigger than Vs1, then the speed for Vs2 is bigger than the speed for Vs1. The second method for speed control is the field winding control. The flux is inversely proportional to speed, and we have EA and the K are constants, then increasing flux will decrease the speed. We have phi 2 is smaller than phi 1, then at a smaller flux, the speed will be higher than at a bigger value of flux. The two ranges for speed control. The first range is the armature voltage control, which is the speed control for a speed below the rated speed, and for speed higher than the rated speed and smaller than the maximum speed, we use the flux field control. The armature field control is only viable for speeds below the rated speed, whereas the speeds below the rated speed we have, beyond the rated speed or higher than the rated speed, field control will be acceptable solution. For the ranges of speed control, we have the ratio between EA at conditions phi 1 and omega 1 divided by EA at different conditions, which is phi 2 omega 2. If we need an induced EMF at different condition, we can substitute in this equation for linear and nonlinear regions. We can substitute omega with 2 pi n over 60, and we here 2 pi n over 60. 2 pi over 60 is cancelled with 2 pi over 60. We have E over E equals phi 1 n1 divided by phi 2 n2, where n is the speed in revolutions per minute. For the torque, we have torque 1 over torque 2 equals phi 1 IA1 divided by phi 2 IA2. For the linear region, we have phi is directly proportional to IF. We can substitute phi with IF1 omega 1 divided by IF2 omega 2. We have EA divided by EA equals this ratio. And for omega, we can substitute it with 2 pi n over 60. We have EA1 divided by EA2 equals IF1 n1 divided by IF2 n2. For the torque, divided by the torque, we have IF1 IA1 divided by IF2 IA2, and this is viable or valid for the linear region of the flux. For the separately excited DC motor, we have phi is constant, then torque 1 over torque 2 equals IA1 divided by IA2. For the DC series motor, we have the torque divided by the torque equals IA divided by IA all squared, or IA squared divided by IA squared. Now we will begin to see the permanent magnet DC motors. A permanent magnet DC motor is similar to an ordinary DC motor, shunt motor, except that the field is provided by permanent magnet instead of salient pole wound field structure. The construction, permanent magnet DC motors are supported by cylindrical steel stator, which is the outer frame. It serves as a return path for the magnetic field. And for the rotor, the armature has winding and slots as the rotor of the ordinary or the conventional DC motor, and the brushes also. There are three types of permanent magnets used for such motors. The material used has residual flux density and high coercivity. It must have very high residual flux. The first type is Alinco magnets. They are used in motors having ratings in the range of 1 kilowatt to 150 kilowatts. And the second type is ceramic or ferrite magnets. They are much economical in fractional kilowatt motors. For rare earth, the third type, rare earth magnets made of samarium, cobalt, and neodymium iron, cobalt, which have the highest energy product. Such magnetic materials are costly, but are best economic choice for small as well as large motors. The working principle of this type of motors, most of these motors are usually run at 6 volt, 12 volt or 24 volt DC supply obtained either from batteries or rectified AC supply. In such motors, the torque is produced by interaction between the axial current carrying rotor conductors and the magnetic flux produced by the permanent magnet. The same for the electromagnets, but here we have the flux originating from permanent magnets. The performance curves of such motors, the speed torque curve is a straight line. We have the speed law curve is approximately a straight line, which makes the motor ideal for servo motors and the input current increases linearly with the load torque, the efficiency of such motors is higher as compared to wound field motors because in this case we know we don't have copper losses in the field. Then the efficiency of this type of motors is higher than the wound rotor, the wound field motors. Speed control, since the flux is constant, only the control of the speed can be done using the armature voltage control. We don't have field control method. Armature field control can be obtained using armature rheostat or electronically using chopper circuits. Such motors are found in systems where speed control is can be only below the rated speed. Only below the rated speed. Advantages of this type of motors is in very small ratings, use of permanent magnet excited results in lower manufacturing cost. Lower manufacturing cost as compared to the wound field motors. In many cases, permanent magnet DC motor is smaller in size than wound field DC motor of equal power, smaller size. Since field excitation current is not required, the efficiency of these motors is generally higher than that of wound field motors, which is higher efficiency. And for low voltage permanent magnet DC motors produce less air noise compared to um, the counter type of the wound field. When designed for low voltage, which is 12 voltage or less, these motors produced very little radio and TV interference with the radio signals or the TV signals. The main disadvantages of this type of motors, since the magnetic field is active all time, uh, when motor is not being used, the motor are made totally enclosed to prevent their magnets from collecting magnetic jump. Any material which is a ferro material can be attached or attracted to this type of motors from the neighborhood. Then these type of motors must be enclosed, totally enclosed to prevent the magnets from attracting magnetic jump. As compared to wound field motors, their temperature tends to be higher as the flux is always uh, present. However, it may not be much of disadvantage in situation where motor is used for short intervals. If the motor is used for short intervals, then this is not a disadvantage. A more serious disadvantage is that the permanent magnets can be demagnetized by armature reaction. The armature reaction can demagnetize the field winding. Then the magnetomotive force causing the motor to become inoperative. Demagnetization can be result from improper design or excessive armature current caused by a fault or transient or improper connection in the armature circuit, improper brush shift, and temperature effects. Uh, for the applications, small 12-volt permanent magnet DC motors are used for driving automobile heaters, air conditioner blowers, wind shield wipers, windows, fans, and radio antennas. Can be used for electric fuel pumps, marine engine starter, wheelchairs, and cordless power tools. For industry, the toy industry, which uses millions of such motors, which are also used in other appliances such as toothbrushes, food mixers, ice crushers, portable vacuum cleaners, shoe polishers, and also in portable electrical tools such as drills, saws, and hedge trimmers. These are different applications: prostatic limps, wheelchairs and mobility scooters, infusion pump for infusing the fluids inside human bodies, for surgical robots, infusion pumps, patient lifting devices, ventilators in ICUs, for continuous positive air way pressure, which is single set pressure throughout sleep for the ventilators, and for the bi-level positive airway pressure, two distinct pressure settings for inhale and exhale. Also, we have dental chairs, syringe pumps, and this is the end of this lecture. See you all in the next lecture. Goodbye.